See? Proof. She's always going in to hit me.
You keep talking like that. She might actually do it one of these days.
Good afternoon, ladies and gentlemen. Dr. John Belkwitz here from Intelligent Concrete. We just had an awesome day of making and breaking, or was that yesterday? We're discussing concrete today. We've got some great questions from our YouTube subscribers. Thank you, One High Voltage One, ding, for this awesome question. And then, before I go into this question, I'm retracting the ding. We've been getting a lot of requests on our comments within YouTube. I think the last one was from a gentleman named Hans, to put a little bit more substance behind the things that we're talking about. So while I'm talking about this, Haley is going to be doing the math that I'm doing, because you got to do it while I'm doing. So Haley's going to be doing the math, and we're going to, what do you call it, Haley? Overlay the audio? Is that how, is that really how it's?
A voice audio overlay audio.
Voice. Really? That's how you call it? I don't believe you. All right, so let's get in it. Ding! One High Voltage One. Thank you so much. We're coordinating that steak dinner for you in Belgium. When your makeup water is high on the nitrates, will it act as an accelerator as well? I'm comparing it to sodium and calcium nitrate accelerators in the video. So, One High Voltage One, Thomas, we ran the math on this to really just understand the numbers. And we used two concepts, either that the water that you were using was potable or it was non-potable water. And we'll get into that here in a moment. But let's start out on the math. So, we're going to do this more in English or in American units. Some of the units we're going to, I'm trying to go slow here because Haley's already getting started. Some of the units we will convert for you, but bear in mind this is mostly in American stuff. So if we assumed that our weight of cementitious was, and let me back up, what we're doing here is we're determining how much solids are we getting from our calcium nitrate accelerator, making certain assumptions about the concrete. So the weight of the cement is 564 pounds per cubic yard. If I convert that, 564 divided by 1.6855, that's 335 kilograms per cubic meter. That's for you, Thomas. So we're going to go back to our American unit. So we're at 564 pounds per cubic yard. That's 5.64 cement hundredweights. Now, the reason why that's important, just like the European units, when we dose our accelerators or liquid accelerators, we use fluid ounces per hundredweight. So most of our non-chloride accelerators, the starting dosage is around 1%, which can be anywhere between 12 and 18 ounces, fluid ounces per hundredweight. We're going to be using 12 fluid ounces per hundredweight for our dosage of our calcium nitrate accelerator. So if we multiply 12 fluid ounces per hundredweight by 5.64 hundredweights, we get just shy of 68 fluid ounces per cubic yard. Okay? Now, converting that over to milliliters, and you'll see why in a second, take 68 fluid ounces per cubic yard, multiply it by 29.57 milliliters per fluid ounce. Our fluid ounces cancel out, and we're left with milliliters per cubic yard. Okay, sorry about that. We had a little bit of technical difficulty, but it seems like we're back on track. So we multiplied that 68 fluid ounces per cubic yard times our 29.57 milliliters per fluid ounce, and we came up with 2,001 milliliters per cubic yard. Now what we're going to do is we're going to multiply that 2,000 milliliters per cubic yard times the specific gravity of our non-chloride accelerator, which, looking up online, we found most of them were somewhere between 1.9 or 1.8 to 2.5. So we settled on 2 grams per cubic centimeter, and cubic centimeter is really just a milliliter. and cancels our milliliters cancels out, and we're left with 4,002 grams per cubic yard. Now here's the thing, that's the weight of our liquid. Most of our non-chloride accelerators are not 100% solids. They're somewhere between 40 and 60% solids. We chose 40% solids. So when you multiply 4,004 times 40%, you're left with 640 grams of calcium nitrate per cubic yard. So using our 12 fluid ounces per hundredweight for our 564 pounds per cubic yard, or our 780 milliliters per 100 kilograms of cementitious and our 335 kilograms of cementitious, we have somewhere around 640 grams of calcium nitrate per cubic yard in our case here. And that's what's really going to kick off those thermokinetics of cement hydration to get us our early setting or early hardening time. Now, going back to Thomas's question, can we get that from potable water? So this is our potable water version of it. So when I say potable water, I'm assuming that the maximum calcium nitrate that we're allowed to have is 45 milligrams per liter. So if we're doing the math through that, assuming that we have a 0.45 water cementitious ratio, 564 pounds per cubic yard times 0.45 on our water cementitious gives us 254 pounds per cubic yard of water. So 254 pounds per cubic yard of water, we got to first convert that to gallons, right? So 254 pounds per cubic yard divided by 8.345 pounds per gallon of water gives us 30.44 gallons. Now converting gallons, 3.78 liters per gallon, so 30.4, that gives us, oh my goodness, that gives us 115 liters. And again, remember, we're still in cubic yards here, so a little bit weird. Now, the reason why we converted it to liters, because remember, we're dealing with micrograms, or excuse me, 45 milligrams per liter. So now all we have to do is multiply 115 liters, which is on our cubic yard, times 45. Now remember, it's milligrams. Times 45 milligrams per liter. We're left with 5,175 milligrams. Now, we weren't dealing with milligrams. We were dealing with grams before, so we've got to divide that by 1,000. So, for that 45 milligrams per liter in our liters of water, we don't have the 640 grams of calcium nitrate. We actually have just a little bit over 5 grams of calcium nitrate. So, to answer your question, Thomas, one high voltage one, no, I don't think you're going to see an impact from the calcium nitrate from potable water. It's just not enough. Well, then the second scenario is, okay, if that's not enough, how many milligrams do we need per liter of water if we have this many liters of water in our concrete to see that impact? So we know that we have 115 liters. I use black because this is the other scenario. So this is what we're working with. You can consider this non-potable water. This water you should not be drinking, and that's not far-fetched because there's a lot of ready-mix providers who are trying to recycle and use their reclaimed water, put it back into concrete. So this is a very good question. So this is non-potable water. We know we have 115 liters in our cubic yard, and we know if we went with our 12 ounces per hundredweight, we were going to get somewhere around 640. Is everything okay? 640 grams of calcium nitrate from our liquid admixture and our cementitious. So if we go back to what we know is measured from our potable and non-potable water, it's in milligrams. So if we have 640 grams, we actually need, multiply that by 1,000, 640,000 milligrams of calcium nitrate in our 115 liters of water. So 640 times 1,000 gives us 640,000. Now, no, just 640 milligrams per cubic yard.
Mm-hmm.
Now we know we have 115 liters, so if we just divide that by 115 liters, we'll find out how many we'll need per liter. 5,565 milligrams per liter. Huh. That doesn't work out.
Hmm.
64000 divided by 115. 5,565. And then that only comes out to... Oh, no, that's right. I'm sorry, that is right. Because our... Ow, son of a biscuit. So our potable water was only 45 milligrams per liter. So if we divide this by 45, we're effectively 124 times what we would need in potable water to see...
That's the maximum in potable water.
That's the maximum in potable water. So we would need to be 124 times the maximum allowable calcium nitrate levels in our potable water, which of course means we're non-potable, but to see some sort of an impact. Now, that would be 12 ounces per hundredweight. You know, I mean, the argument could be made, maybe you don't need that much. Maybe you need half or 25% of that. But the fact remains is, you know, with 45 milligrams per liter, you're just not going to get enough of those solids in there to kick off those thermokinetics of cement hydration. So hopefully this helped out. Haley, thank you very much for including the substance, doing the math for us. Don't forget to like and subscribe. Ding that bell for notifications. Go Concrete!